Good evening, everyone. So, welcome to the NPTEL course of Carbon Materials and Manufacturing. And we have reached in the week 10th of the doubt and problem solving sessions in this course. So, I'm Saurabh Soni, and let's begin with the doubts and the problems related to the lectures which has covered in week 10. So the flow of this lecture would be, firstly I'll give you some concepts which will be helpful to solve your assignments and problems in which has been given in your assignments. And after that I'll be discussing some problems which I have gathered from the lecture of this week, and hopefully this all concepts as well as the questions that we'll be taking at the end of this lecture will be helpful to clear your doubts and will be also helpful to solve your assignment number 10. So yeah, let's begin. So let me take my pen. Yeah, so yeah. Okay, so in the last lectures we have covered some CVD techniques and the many manufacturing techniques of the synthesis of many materials. So this week we'll be starting again from the same. So the firstly the boundary layer. So you have heard this term in CVD process. So I have explained you CVD in the last lectures. If you have not recalled it, then please see the last lecture. So whenever you do the CVD, there is a substrate, and close to the substrate, the gas velocity are nearly zero. Okay, so let's say you will do, and here is your substrate, and so near to this substrate, the gas velocity are nearly zero, and this influence the mass transport of the carbon species. Okay, so if the gas velocity is zero here, this will affect the overall mass transport. So this will affect the mass transport of your carbon species in the CVD process. So if your boundary layer is thinner when the pressure is low, okay, and the diffusion coefficients are large. So there are some, steps which limits the rate. So in CVD process, the first thing is your reaction kinetics limit, or you can say the rate limit. So common in low pressure or low temperature system that do not facilitate a fast reaction. Okay, so where it has used, so where you require a low pressure, okay, or let's say a low temperature system. Okay, so where your fast reaction process would not be facilitated, right? And the this one is your first, and the second is your diffusion limited, right? So here the temperature will be high in the system with thick boundary. Here the boundary will be thin, but here your boundary will also be a thick. Now the boundary layer decrease the rate of diffusion because it is thick of the generated species into catalyst. Desorption of byproduct is also slow. So here also the increase in flow rate, concentration and residence time of gases can increase the deposition rate. Okay, so if you want a higher deposition rate, then flow rate, you have to increase the flow rate. Okay, concentration and residence time of gases. Okay, so the concentration and the residence time of your gas you have to increase in order to get the higher deposition rate. Tilted substrate can be used for minimizing the boundary layer effect. Okay, so you will get, so here you can say, in this case here this is a flat, but here this is your inclined substrate. Here you will have a flat substrate. Okay, flat substrate, but here you will have an inclined substrate. to avoid boundary layer effect, right? So in this way you can avoid the boundary layer effect. So here you can see that this Reynolds number is given by your formula rho v d upon mu. So what is rho? Rho is your fluid density, mu is your fluid velocity, mu is your fluid viscosity, d is your length, and this is your yeah. So here you can see delta is L by R. So this is your boundary layer thickness. Okay, so here you can see this is your boundary layer thickness. Okay, and this distance along the substrate. L is the distance along the substrate. So now here you can see the your boundary layer thickness is higher, right? But when you tilt, the boundary layer thickness will reduce when you tilt the substrate. Okay, we'll see some numerical also in the last regarding this how to calculate. Okay, so I hope it is clear. Okay, so it's fine if you don't have any doubt, and let's go ahead. So now we have seen enough of our CVD process, how it take place, and what are the parameters that affects the deposition rate, and how can we use for the different kind of a deposition, and what are the materials that we can use here. Now here the main thing that in the carbon material is your graphene, that we have already covered, that how the graphene is and what are the structures and how it can be used for the many different applications and what are its different and unique property of this material. So now if you want to do the chemical vapor deposition of your graphene material, then what could be the mechanism when you want to do the CVD, and how you can control the parameters in order to get the better deposition by CVD techniques. Okay, so now the main thing is your parameter that matter. Okay, so whenever you do the CVD, there are some parameters that you need to optimize, or I should say that you have to control or the monitor throughout the process. So here the first thing is your temperature. Okay, so why temperature is very important? Okay, so every material has some unique property and that changes along with the temperature, right? So if you want to deposit at certain if you want to have some particular deposition rate, okay, then you need to change or you need to control the temperature accordingly, right? You have to monitor or optimize. You can't certain I mean you can't directly give any particular temperature. Okay, so for any material, let's say it could be a graphene, it could be a CNT, it could be a normal your semiconducting materials. The second is your pressure. The same thing, when you apply the pressure, so at different pressure, your material behaviors changes. Okay, so that's why you have to keep optimizing and control your pressure. Gas flow rate. Gas flow rate. So what is gas flow rate? Basically, when you do some process like CVD and all, there would be gas inside. Okay, so you have to control that gas in such a way that it should, I mean, the concentration of the gas which is going inside of your chamber, that should be controlled. It's not like the gas particles are more inside, and sometimes it is less than the desired amount. So you have to optimize the gas flow rate, that what it could be. The next is your catalyst. So in order to start any process, you require a catalyst. So you should know that what kind of a catalyst it is, what are the size you are using, what are the shape that you are getting. So that also affects your depositions when you do the CVD. So that's why any catalyst, if you are using, you should know that which type and what are its shape and which size is giving a better deposition. The next is your precursor. So in the precursor also, it is also important because you should know that what are its size and shape and what kind of a precursor you are using. The next is your defects or vacancies on catalyst surface. Suppose if your surface is having some vacancies or the defects, right? Then when you will do the deposition, it won't, you know, come in a desired way that you want because it has a defects, existed defect. So that also you should know that till how much percentage of defect is acceptable. If that is more than that, then it is not advisable to do or to perform the experiment. The next is your poly or monocrystalline structure. Poly or monocrystalline structure. Any material you are using, you should know that whether it is a polycrystalline or the monocrystalline. So that's also related to the your how it will affect the process, because if it is a polycrystalline, then there will be a many the structure is different. Okay, the shape and size will also change. So that's why the main structure that you want, that will also affect your deposition. So the exact effect of each parameter must be established. Okay, so if you want to do the CVD, you have to control this all effect if you want to do your deposition in a certain desired manner. The exact effect of each parameter must be established. Reaction. What can be the reaction? The pyrolysis of precursor hydrocarbon. Okay, here you are using a precursor as a hydrocarbon. Hydrocarbon. So you have to control the pyrolysis. Okay, so here your reaction will be your pyrolysis of your material. Okay, any doubt? Clear? If you have any doubt, you can ask. The commonly used hydrocarbons for this process. So, what precursors we can use? What are the hydrocarbons we can use here? Is methane, acetylene, ethane, light, and some light hydrocarbons. Okay, so the reaction does not necessarily yield carbon atoms or radicals. Many other forms of carbon, including C2, C8 molecules, carbynes, other possible vapor phases, species may be present. Some of them are very short lived and some of them are metastable. So now when we use these hydrocarbons as a precursor, then it will go under the decomposition. Okay, then there will be the formation of the radicals and the partial crystallizations will happen. Now after this there are, I mean, many larger hydrocarbons would also be there present, like such as your benzene, naphthalenes. Okay, so that may also be other larger hydrocarbon could be present. So this is all about the precursors that we can use, like a methane, acetylene, and some light hydrocarbons, ethane, methane. So okay, now the which we have heard here is the catalyst. Catalyst is also play an important role in your in your deposition process, such as your what kind of a catalyst you are using, what are its shape and size. So generally, the catalyst material we use is your transition metals. Okay, so what are the transitions metals? So when you will see in your periodic table, there would be a list of transition metal, but here mainly we can use some copper, iron, copper, and your iron, platinum, nickel, iridium, ruthenium, platinum, and many more, and various alloys can also we can use. So we can use this as a catalyst. Okay, so here we have covered that what could be the catalyst and what could be the precursors that we can use here for the CVD of graphene. Now the graphite and other forms of carbon can also be used for deposition. So since here we are mainly dealing with the graphene, so it is not only bounded or the limited till graphene. There are some other types or the forms of the carbons that we can use for the deposition. So what could be that form, such as your graphite, it can be your carbon nanotube, and many more. Okay, that we have dealt in with in this uh, course. So that also you can deposit by using this method. It is reported that nickel enables slight penetration of carbon species before their precipitation, while copper based reactions are surface bounded. Okay, so here you can see when you will be using nickel as a catalyst here. Okay, so here you will have the penetration. Okay, okay, in case of nickel, but when you will be using the copper, you will only be getting the surface bound. Okay, it cannot be penetrate here. Okay, while in this case it can penetrate the surface. When you use the nickel, it will enable the slightly penetration of the carbon species before precipitation, while in case of copper it cannot be found. So is it clear, or do you have any questions? And if you have seen any kind of a more precursor or the catalyst, then you can also share and discuss. So now in the CVD of graphene, um, so in the same league of the parameters and what could be the mechanism that we can use here. So here you can see the solubility of carbon in metals. Okay, so the first thing is the solubility and diffusivity of carbon plays a very important role. Okay, in what? So first you are optimizing the deposition temperature. Okay, deposition temperature is very important, as we have discussed. This is the temperature is very important parameter during the depositions. Second is you are controlling the film morphology. Okay, so it is very important to see that what is the morphology that you will get, that should be controlled. Okay, so to controlling and optimizing this, the solubility and diffusivity of carbon plays an important role. So at around 70 750 degree centigrade, the diffusivity of carbon in nickel and palladium is in the order of 10 is to power minus 9 centimeter square per second. Okay, so when you will use nickel, then the solubility of carbon diffusivity is 10 is to power minus 9 centimeter square per second. But similarly, when you will be using the platinum or the ruthenium, then here it is in the range of 10 is to power minus 7 centimeter square per second. So there are still several open questions related to the mechanism of your graphene CVD. So here you can also see this is the solubility here. So when you will be increasing the temperature, okay, so initially the solubility will decrease, okay, and then it will increase. So here you can see when you will go to the high temperature, the carbon solubility in the gas phases is increasing. So here 10 is to power minus 2, 10 is to power 2 bar, okay. So here the the boundary limitation can be overcome by patterned CVD substrate or not. Should the catalyst be in a liquid phase? It is necessary, or it could be any such as your solid or gas or any form. Are byproduct cyclic structure forming in the gas phase or also on the catalyst or both? So here these are some open questions that you can do your research in this field, or you can have some literature. This is very good and interesting questions, and it will give you more and more informations when you want to do the CVD. Suppose here we have seen the catalyst such as nickel, palladium or some platinum. So can we use liquid phase of this catalyst? Is it okay? Or if suppose if we will be using, then how the deposition process will take place if we will be using the liquid phase, okay. And the boundary limitation be overcome by patterned CVD substrate. Okay, suppose if you are using a CVD substrate as a flat or it could be inclined, but let's say if you are using, if you are making some pattern, then the boundary limitation could be overcome or not. Okay, so these are some open questions that you can do experiment and get back to this, and also you can have some literature. I believe that there could be some many good papers you can find on this. And also there are some byproduct and cyclic structure forming in the gas phase are also on the catalyst or both, okay. So if you want to have some good observation and the good knowledge of this, you can refer to these books. These are some learning books. So here you can see the handbook of CVD. Here you can get how the parameters and the mechanism and what could be the parameters which affects the deposition of a material. So here you can also find, and the NPTEL lecture by your Professor R. Nagarajan in Principle of CVD Process, and Indranil Manna, Surface Engineering for Wear and Corrosion Resistance, Professor Kaushik Pal, Surface Engineering of Nanomaterials. So these are some of the lectures and this handbooks. And apart from that, you can also see some good journal paper refer. There you can also find that how it can affect your deposition. So I hope it is clear. And if you have any questions, then please ask. We can solve your doubts. Now, so when you will do any kind of a deposition and also what could be the defect that can be we can found in your 2D material. So right now we have seen enough of what CVD process and what could be the parameters and the mechanism we can use, and now we will see that the defects in what are the defects present in the 2D carbon materials. Okay, so here as we all know that in the defects in the general concept of defects we have seen in what could be the defects like your point defects, line defects, surface defects. Yeah, so these are the some kinds of defects that we have seen. And if you do not know the concept of defects, you can refer any introduction to material science book. There you can find the defects. So here the 2D carbon sheets may contain non-hexagonal rings as point defects. Okay. So in the 2D sheets, it's not always be a hexagonal. It can be a non-hexagonal kind of a sheet that you can refer as a point defect. Now, the defects influence the properties of a single layer by introducing, for example, different chemical reactivity. Okay, so when the defect is present in your material, then it can affect sorry, if the defect is present in your material, it can influence the many properties of your materials. So that's why the amount of the defects present in your material is also required. That's why in our previous process CVD we were optimizing and controlling all the parameters such as catalyst, precursor, pressure, temperature in order to get reduce of the more defects. Okay, so here also we can it can influence the chemical reactivity and more properties. Now the graphene is a good experimental model to study the defects in tube material. Okay, so since a very basic questions why this graphene is a very good example, since we have covered that the graphene is a 2D a single layer 2D sheet. Okay, so it is the best example of studying of a 2D material. Okay, so how you get the graphene, that we have also seen graphite is a multi-layer of graphene. Okay, so when you extrapolate the graphite, and when you will get the single layer of your 2D material, then this graphene is very good. Okay, good for study the defects in the 2D material. Now they are induced in a controlled manner. Most of such studies are conducted. Just a second. So most of such okay, so the graphene is a very good example if you want to conduct an study of the 2D material, because it is a single layer 2D sheet. So we have seen enough of that how we can get a graphene by extrapolation of your graphite, and there are some many more method or some industrial grade also. So the most of such studies are conducted using TEM or STM. Okay. So the first of all, why TEM? Okay. So TEM. So this is one of the very amazing and very good imaging technique in order to analyze or observe the deposition or the distribution of your atoms, or you can see a single layer atomic sheet. So by TM you can observe that how your carbon atoms are arranged in a particular manner. Okay, since the graphene is our 2D material, and here the mostly the atoms are arranged in a hexagonal flat system, packed system. So it can be easily observed by using your TEM. Okay, so TM and the STM is also the same, scanning tunneling microscopy. These two methods can be used to conduct the studies of a 2D material. Electron beam can also introduce defects, right? So suppose, especially in the case of few layer structure, so suppose it is also important because it is just a single layer or a very thin sheet. So thin sheet, so when you will be using any electron beam or kind of a techniques that can also affect the structure if you have a very thin single or few layer. Okay, so it can also introduce or induce that defect in your material. So overall, if you will see in a nutshell, there will be a five kind of defects which is present here. The first one is your Wells defect. The second one is your single vacancy defect. Third one is your multiple vacancy defect. Fourth one is your line defect. Fifth one is your carbon additives. Okay, so we'll see what it is and how it can be introduced and how it looks and how it affects the properties of your material. Okay, so I think you have known like this vacancy defect or the line defect or the carbon atoms overall. If you have seen the little bit of the type of the defect in your basic material science course. So do you know that we have seen in usually in the metallurgy and material science, we have seen the grains, formation of a grain and the grain boundary. So grain boundaries is also a type of a defect. Grain boundary. Do you know that this is also a defect? Okay, so since it also sometimes that's what I was saying. Whenever you are using any parameters and a precursor and catalyst, it is very important to control the defects. Grain boundary is important to present in order to get the particular strength. But if you have a very large amount of grain boundary, then it can deteriorate the property of your material. So this is also very important. Okay, so that's why. I'm saying that I mean, the grain boundary line defects include the grain boundary is a type of a line defect. So, however, one must be careful if the grain boundary is with one layer or that form another layer. Okay. Now, uh, okay. So the asymmetry. may also be distorted. In some cases asymmetry means we will see in our further structure how we can, it's like a zigzag kind of a structure. So here you can see the boundaries of your carbon material. So this is your mainly boundaries. Okay, so if you will change the focus, then here you can see this boundary may disappear when you will go to here, and only you will see is this boundary. Okay, so this is basically if you will analyze this, it could be like this. So if you will see from this side, you will only get to see the this, but if you will see from the top, you can see this boundary also. Okay, so there are your two boundaries, but here you can see only one, but in this case you can see. So here extremely thin sample it is, and when you will change the focus, okay, you can see the different boundaries. So this is how you can see the difference in your carbon material. Is it clear, or should I explain it more? So now you can see in the slide many kind of defects here. So in the first one is your stone wells defect. Okay, stone wells defect. So here you can see in this area. So it is not making a hexagon. It is mainly like 1, 2, 3, 4, 5, 6, 7. Okay, so and here it becomes reduced 1, 2, 3, 4, 5. So that's why it is affecting the nearby packing also. Okay, so here it's not a completely hexagon kind of a shape. Here some are more than 6, and some atoms are packed with more than less than 6 atoms. Now the single vacancy, so by the name itself it is clear. So here you will vacate. Here the one atom is your not present. So here it can make something like this, but here and like this, but here your atom is not present. Okay, so that's why it is your single vacancy. Add atom, so in the add atom it's like this, but here you have a this, here will be your, it is not in a complete, here it is less than 1, 2, 3, 4 and 5. So here one atom is your missing, so one atom L atom defect. Here also you can see it is more than 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is also not in a shape. Same thing is here. This is a double vacancy. This is a single vacancy. Here you can see a double vacancy, and this is same also. Okay. So these are some structural defects in graphene like carbons. You can find many more. So these are the defects. Now you can see the line defects, so the dislocation, how the dislocations can be present. So here you can see since in this atom in this pack you can see 1, 2, 3, 4, 5, 6, 7, 8, sorry 7, one more atom. So here 1, 2, 3, 4, 5. So here you will have this edge effect. Okay, so it won't in other side you can find it like this, but here it won't go like this. Here 1 0 dislocations will be present because the Berger vector here you can see is 1 0. Here your Berger vector is what you can see the previous lectures here. Then you can find 1 1 will be your Berger vector. In this case your dislocations is 1 0 and 0 1 dislocation. Okay, because your Berger vector here you can see. So this is like your edge effect and the line dislocation, edge dislocation or the line dislocation. So in the mainly line dislocations you can see the edge dislocations and the screw dislocations. Okay, so these are some defects present in your graphene. Now we have seen the graphene, how the defects are present and what are the parameters, how we can optimize and how we can deposit by using our CVD techniques. So now the next is our CNT. So we have seen the hybridization. So hollow filaments of sp2 hybridized carbon sheets that may be a single wall or the double. So CNT is also single walled CNT and multi-walled CNT. These are the two types of CNT present. Okay. Such structures often observed on outer surface of blast furnace and were also reported in scattered publication in 1950. CNT are closely related to spherical fullerenes. Okay, so if you have seen, this is like a spherical fullerene and this is a tubular fullerene. So it is somewhere related to your spherical fullerene and are a type of curved carbon structures. So efforts to make tube-like carbon structure accelerated post-Fullerene discovery in 1985. So history of CNT discovery development can be found in various publications. So here you can see the TM image of carbon nanotubes published in 1952. So this is, you can see how beautiful it is, like a tube kind of a shape. This is also like a tube. So the hybridization in CNT is not pure sp2, but rather than it is a sp2 plus n. So we have seen that sp2, sp2 plus sp2 plus n, sp3. So it is not sp2, it is sp2 plus n due to their curvature. Okay, so in the very initial lecture, I think in the second or third, we have seen the hybridization present in this all the carbon materials and how it changes from sp2 to sp3 due to its curvature. So it is very one of the mainly used and it can be used in many kind of applications. So CNT are used in the electronic, in the field of electrochemical, field emission, or basically mostly it is using nowadays in optoelectronic and for the sensor devices because of its unique and amazing property. It is a conductive material as well as also it has a good mechanical strength. So that's why we use this for the optoelectronic and the sensor devices. CNTs and CNT ropes are used in composites. Okay, so also we use this kind of a CNT we can use in the form of a composite. We can mix with the other materials in order to enhance the property. Okay, so in this way we can use our CNT material for many kind of applications. Okay, so any questions? And if not, if you cannot recall the hybridization, you can watch the previous lectures that we have discussed earlier. Maybe I think in third or fourth class I have explained this hybridization pattern. So now the classification of carbon nanotubes. So carbon nanotubes can be classified based on there are some parameters. So the first one is your um number of walls. Okay, so whether it is a single wall or it is a multi wall. The second one is your chirality. Okay, so with or without mirror symmetry, there are some CNT that are chiral and they are non-chiral. Third one is your depends on its conductivity, or you can see the electronic property whether it is a highly conductive or whether it is not conductive. So it can be in a range of a semiconductor. Capped or open. Okay, so this is something that maybe you might not know. So the capped or open, that I will tell you that what it is. So here the achiral or chiral. So firstly, I think in your plus one or plus two, you might have heard that what is chiral. Chiral is a molecule that cannot be superimposed on its mirror image. Okay, but achiral is something a molecule that can be superimposed on its mirror image. Okay, so zigzag and armchair CNT is a majorly the example of your achiral, and chiral is other than the armchair and the zigzag. So here in the zigzag you can see you will mainly find this zigzag kind of a shape here. Okay, here when you will see that. So this is your zigzag. Okay, this is your SW single word and this is your multi word. Here you can see a different wall. So this is your multi word. This is your single word CNT, multi word CNT. Now the circumference of CNT defined by chiral vector C. Okay, chiral vector. So in the armchair here you can see that this is not like a zigzag. It is like this is mainly like this. Okay, but in zigzag it is mainly like this, but it is not like this. Okay, it is like this. So the circumference of CNT is determined by this chiral vector C, which is NA1 plus MA2, and here the R is given by C upon 2 pi equals to root 2 upon 2 pi a n square plus n square plus 8 nm. So for single wall can be metallic or semiconducting, and its band gap is ranging from zero point 0.4 to zero point 0.2 electron volt, and the MWCNT is typically metallic because they are larger diameter. Okay, so I hope that it is clear that what is chiral and achiral, and how the multi-word and the single word looks, and uh, what could be the properties it given, and how the electronic properties also uh, depends on the single word and the multi-word. Okay, is it clear? Now we'll see that the CVD of carbon nanotubes, as we have discussed the CVD of the graphene material. So yeah, now the common fabrication methods are here. So the arc discharge may be combined with catalyst co-vaporizations. So arc discharge is a very common fabrication methods. Okay, so the first one is a arc discharge. Okay, so inducing very high voltage difference between two graphite electrodes here we use, and we induce a very high voltage between those two electrodes such that the plasma could be generated. Here the yield is relatively low and high tube formation temperature is required. Other fullerenes and curved carbons are co-produced, both multi-volt and single volt CNTs. The second is first one is your arc discharge. So here we applied a high voltage between two electrodes. The second one is your laser ablation. So in the laser ablation, what we do, we irradiation of graphite with highly intensity laser, or I should say the high intensity laser. It is more suitable for the single wall CNT formation temperature lower than the arc discharge, because here it can vary depending upon the laser parameters also. Since in the arc discharge we use a very high voltage, here we are using a high intensity laser. So it depends on the intensity of the lasers that you are using, the temperature can vary. The third one is your, apart from this, is your main technique, which is CVD. So CVD is a very low cost. I mean, it's not very expensive as compared to the laser and all, and it is a very easy method, and that's why we can use this methods for the large scale production or the bulk production of the carbon nanotube. So the basic principle, it is similar to the graphene that we have discussed earlier. So in this case also, like the main parameters required is your precursor, catalyst. Okay, so precursors also here, what we can use as a precursor: methane, benzene, acetylene, etc. And catalysts are used in the form of particles here. Some most commonly used catalysts here, in earlier we have used the transition metals as a catalyst in case of graphene. Here some magnetic metals such as your, okay, let me write magnetic metals, what could be like iron, cobalt, nickel, etc. So these are the most commonly used catalysts in case of a CVD of a carbon nanotubes. Now, the noble metal catalysts are also reported. Such metals are generally not used for hydrocarbon cracking. Metal oxide, silicon, and other conductive substrates are using for supporting the catalyst. In case of conductive substrate, if you use any substrate which is conductive in nature, one can use a diffusion barrier between the catalyst and the support. Now, the mechanism, CVD mechanism of our CNT, like we have seen the CNT mechanism in graphene. So to here in the CVD mechanism of CNT, two theories exist for the CNT formation mechanism: vapor, liquid, solid mechanism. Okay, this is very important in CVD. So what we call in a short form VLS method or VLS mechanism. It means the vapor, liquid, solid. So if you want to know the very detail, then you can see any uh, deposition CVD deposition techniques books that I have shown you in the previous slide. That would be a good if you want to learn it better. So the hydrocarbon pyrolysis takes place post adsorption on the catalyst surface to yield atomic carbon. So after this, atomic carbon forms a solid solution with catalyst. Third one is a intermediate carbide formation will occur, and fourth one is a carbon is precipitated in the VLS mechanism. But in case of vapor, the short form is your VSS, vapor solid solid mechanism. So here the pyrolysis reaction take place in a gas phase. Generated species absorb and diffuse on the catalyst and carbon is precipitated. So here there is a no intermediate carbide formation, and there is carbon is directly precipitated after this diffused to the catalyst surface. And here in the case of VLS, there is a formation of a solid solution with a catalyst, but here there is a no solid solution is formation. So that's why that is a liquid solid, vapor liquid solid. This is a directly vapor solid solid mechanism. So the tube grow either from the top. Okay, so here you can the tube can grow from the top to the bottom. From the top or bottom surface of the catalyst. Either it could be from the top or could be from the bottom. This is influenced by the catalyst support interaction or the particle size. Rate of tube growth depends upon the CVD parameters, hydrocarbon concentrations, temperature, pressure, etc. So the rate, these all are depends on the many parameters in addition to catalyst. If catalyst size is too large, one may obtain fibers instead of tubes. Okay, so like the size, type, and the shape of your catalyst matters a lot because it affects the deposition and it can change the requirement that you want. Okay, so here this is your VSS. Here you can see that this is hydrocarbon and this is your this is your hydrocarbon is coming atomic carbon, and there is a precipitate carbon is here. But here in case of this is hydrocarbon, this is your atomic carbon. Now there is an intermediate carbide formation is happening. Okay, and now the precipitate carbon. In this way you will grow the tube. But here there is a no precipitate, there is a no carbide intermediate formation in case of a VSS. Now the vapor deposited diamond. So small diamond catalyst produced by vapor deposition in the form of a film. So hydrocarbon gas is pyrolyzed and used as a source carbon source. Hydrogen is converted into atomic hydrogen which attached to the carbon dangling bond on top surface. Okay, so you can see in the right hand side the diamond one plane, all atoms are chemically identical. So if I would say the H anchoring prevents the diamond 111 plane from collapsing and converting into graphite. Some graphite is also formed in the process. Atomic hydrogen partially etches away this graphite. Atomic hydrogen can only be produced about 2000 degrees centigrade via discharge. Okay, so that's why here if you want to see the 1-1 plane, if you know the basics, so I think so it could be your 1-1-1 plane. Sorry, your I think so this could be your 1-1-1 plane. Okay, so all atoms are chemically identical. So in the arc discharge method is used for the production of atomic carbon and atomic hydrogen. Substrate is typically the part that needs diamond film coating without any catalyst. Substrate temperature are typically 900 degrees centigrade. Hydrogen impurities are often observed in uh, vapor deposited diamond. Presence of oxygen also enhances the film growth. So let's see, I will discuss also some questions, then I will take some more examples. So which among the following can best represent the structure of carbon nanotube. So an infinite sheet of sp2. So I have shown you that what it is. An infinite sheet of sp2 hybridized carbon atoms, a rolled up graphene sheet, a tube composed of sp3 carbon atom. Nano is called football. So it's not a football like, it's not a hybridized and infinite sheet of. So it is a rolled up a graphene, because graphene is a single sheet, but it is a rolled form of that sheet. Okay, so it's like a rolled form of that sheet. So I think so it could be a rolled up graphene sheet, and the hybridization is sp2 plus n. So yeah, it is a rolled up graphene sheet. Single CNT have a much higher Young modulus compared to single carbon fibers, because CNT have lower aspect ratio compared to carbon fibers. CNT can be single or multi-walled, fibers are always multi-walled. CNT have a lower probability of containing defects compared to fibers. The hollow region in the CNT offers resistance to applied. So the CNT have a lower probability of containing defects compared to fiber. So basically, in the fiber there is a more probability to containing a defects, but CNT cannot contain. That's why its Young modulus is a higher. Okay, so that's why this is the right answer. Okay. The formation of single layer or multi-layer graphene during CVD of hydrocarbons depend on the type of catalytic substrate, some temperature, pressure inside the CVD chamber, type of hydrocarbon precursors. So this I have just discussed. If you have know, then it is very simple. The type of catalytic substrate. Okay. So what are the type of catalytic substrate you are using? That is very important. That can give you the whether it could be a multi-layer or the single layer graphene, which I have discussed. In case of cold walled reactor, pyrolysis of hydrocarbon take place only near the wall of the chamber, uniformly inside the entire CVD chamber, very close to the substrate, near the hydrocarbon gas inlet. So this is, I have just explained, it is very close to the substrate. It is taking place, okay, in the cold walled reactor. So this is a numerical questions. So this I would be giving you some hint that probably I will ask you in the next class. Or a substrate of length 2 centimeter is placed inside a tube of diameter 1 inch held inside a CVD reactor. The tube is fed with acetylene gas, a velocity of 0.1 meters per second. The substrate is heated to 700 and growth of some carbon nanomaterial. Calculate the value of boundary layer thickness. Viscosity constant is given. So here, if you will see, I have in the very initial slide, in the boundary thickness, I have explained in the first slide. The formula you can write here. So this is your rho into nu into L divided by mu. Okay. So here you can see that rho is the density of the gas, v is the, this is the velocity of the gas, L is the characteristics length, and mu is the viscosity of the gas. Now if you will substitute this all whatever the given, so rho is how much density is given, 0.0007, and velocity is given zero point 0.1, and your L, how much L is given, 2 centimeter. Okay, so divided by your mu, viscosity constant is given 9.43 into 10 to the power minus 6. Okay, this is 9, this is 0. So how much you will get? The value of your Reynolds number will be your 148.3. Since the Reynolds number is less than the 2300, okay, the flow can be considered laminar. So the flow will be your laminar. because it is less than the 2300. In laminar flow, the boundary layer thickness can be approximated using, so here the formula boundary layer thickness 5 into L upon Reynolds number. So L is here given and 2, it is 2 and divided by 148 by 3. So how much it will come? It will come around 0.068 centimeter, which is somewhere related to the 0.1 centimeter. You can see the 0.068 and or I should write point. So you can also see if this kind of a questions maybe I will in the this we can take in the next class if you will have any doubt or problem, or also like a question and add atom defects in Griffiths implied an additional atom that is present as a manufacturing defect. So I have explained this for different kind of a defect present in the graphene. An additional atom introduced by doping of another element, an electron hole pair generated intentionally, an electron hole pair that is present as a manufacturing. So this is additional atoms, add atoms, additional atoms that is present as a manufacturing defect. Okay, which of the following defect is not possible to exist in graphene? So we have seen the line defects, single vacancy defects, non-hexagonal rings, and stacking fault. Stacking fault is not possible to exist in graphene. When a nickel foil is used as a catalyst during the CVD using methane gas, which of the following is likely to happen? So if you will use a nickel foil, then basically the precipitation of carbon atoms from nickel surface to form multi-layer graphene. Okay. Which of the following are important parameters during the CVD of graphene? So the temperature of heated surface and the chamber pressure and the nature and the type of the catalyst that you are using. So this I have also explained in the parameters and the mechanism. Graphene can be produced by CVD, exfoliation of HOPG. So I think these are the two methods that we can produce the graphene, which I have uh, also explained. So yeah, these are some questions. Maybe we'll try to cover some more questions in the next class. And I hope if you will have any questions, then please bring to the next class. We'll try to discuss this. Okay. If not, then we can go ahead. So yeah, thank you for your attention.